angular momentum. And we basically discussed that when the external torque is 0 or the net external force is 0, in those cases we conserve the momentum. Now the net external force is 0, so we conserve the linear momentum. And when the torque is 0, then we conserve the angular momentum. So we discussed that angular momentum is conserved, and the formula of angular momentum I told you. Remember 4 points I told you about the dynamics of circular motion? These one. Out of this angular momentum is very important. L is equal to I omega. Okay, so dl over dt is equal to 0. This is the form. Means see, when the torque is 0, and torque is basically a conservation of angular momentum. So rate of conservation of angular momentum is itself 0. So dl over dt is 0. So here in this case, L is constant, that is I omega will be constant. Because see, that's the formula of it. And what you do wherever you have, let's say, two bodies are there. You can say first moment of inertia is there, omega 1 is there. The no. Just check my audio, is it fine?
Your voice is breaking.
Voice is breaking. Is it better now, Nabila? Now is it fine or still breaking?
It's still low.
Okay, just check now. Is it fine?
Yes, sir.
It's better. So let's discuss a numerical based on this. This says that a man stands on a rotating platform with his arms stretching horizontally. So this is the example which I told you of the ballet dancer, that they stretch their arms and they bring their arms closer to their bodies. So this says a man stands on a rotating platform with his hands stretching horizontally, holding a 5 kg weight in each hand. Means this hand also has 5 kg, this hand also has 5 kg. Like this, he is holding two weights. And he is standing on a rotating platform. So if he is standing on a rotating platform, obviously he'll also rotate with it. So this is like, this person is there on a rotating platform. Okay. And the arms are stretched and holding 5 kg weight. Then it says angular speed of the platform is 30 RPM, rotations per minute. RPM, I told you, no, rotations or revolutions per minute. Now see, this platform is rotating. So that is not revolution. This is rotation only, right? So 30 RPM is there. So it means this angular velocity with which this whole platform is rotating, this is 30 RPM. This is the man then brings his arm close to his body with a distance of each weight from the axis changing from 90 centimeter to 20 centimeter. Means this separation initially is given as 90 centimeter. Now what has happened? In the second case, see, the person has brought these 5 kgs closer to the bodies. Okay. Both bodies are there and the person has brought them closer. Means the radius now has changed to 20 centimeter. Obviously, the weight will not change, but the radius has changed. Fine. It says moment of inertia of the man together with the platform must be taken to be 7.6 kg per meter square. Like we calculate, no, for disc we calculate, for sphere we have calculated, for cylinders we have calculated, for different shapes we have calculated. So here the moment of inertia is directly given to us, and don't take a disk separately, don't take this. The platform and the man together, the moment of inertia, man is given as 7.6. So moment of inertia is given as 7.6, but this is the inner moment of inertia of platform plus man. This is not the moment of inertia of the blocks, remember. Of these kgs, the weights that he is holding, this is not of it. 7 kg meter square. This is the moment of inertia present. It says what is his new angular speed. See, let's say this is some omega 1 with which. Okay, now here this must be rotating with some omega 2. He says, the question says, find us and tell us the value of this omega 2. I told you, no, in the last class, in the example also of the ballet dancer, that if you stretch your hands apart from each other like this, okay, if the hands are stretched out, then what will happen? When your arms are stretched out, the velocity decreases. So you quickly bring them close together to your body. So radius decreases. When the moment arm decreases, moment arm means the radius, okay? When the moment arm decreases, the angular velocity increases because there is application of conservation of moment. Remember, momentum will be conserved. This is conservation of momentum. Okay, this is the conservation of momentum. Now, see, first we'll calculate the angular momentum of this, then we'll calculate the angular momentum of this, and then we'll equate both of these angular momentum to each other. Now, for angular momentum, basically what have we studied the formula as? Formula is I into omega. Now, omega for everything is fixed because the platform is rotating. It's not like the platform is if the platform was stationary, man was rotating, so platform would have not rotated. Or if we say we would have taken platform speed 0. Entire system is rotating, right? The entire system is directly rotating. So whatever will be the speed of the platform's rotation, person is standing there only. He is holding both of the weights. So both of the weights plus the man, the entire rotation will give us the same value of angular momentum. So angular momentum will be the same of the entire system. Omega will also be the same, but moment of inertia will not be the same. We will not have one single moment of inertia because see what are there in your system. Just identify the things that are present in your system. You have man plus platform plus this 5 kg weight plus one more 5 kg weight. 4 things are there. I'll remove this one. 5 kg weight plus 5 kg weight. Okay, so moment of inertia will be man plus platform. See, it's given to us. Break it like this. We need L1, that is I omega 1. Similarly, here we need L2, which is equal to I into omega 2. We just need to equate, but we just have to calculate the moment of inertia. I will be, see, moment of inertia, these are the 4 things that are present with us. So man plus platform is already given to us. Man plus this platform, they are already given to us, which I have written as IP 7.6 plus. For the 5 kg weight, mass is there, separation is there. That is 90. Let's say this is R1. So this will be M R1 square plus, or no, by R1, you can simply, well, let's take this as R1 and this as R2. And for this, so this done, last 5 kg weight will be plus MR1 square. Now see, you put this net moment of inertia's value here, what we'll get? L1 is equal to IP plus MR1 square plus MR2 square into omega 1. Is it clear till here?
Yes, miss.
This much is fine? Okay, so we have basically calculated the moment of inertia. Okay, see, anyways, this is the moment of inertia. This is the angular momentum of the first one. And angular velocity. So like this one equation is made. Hafsa, could you understand anything? Because you were absent from the few classes. Could you understand anything from here? Hafsa?
No, ma'am. Actually, my half-yearly exams were there, so
Yes,
I'm
that's
not
I'm saying.
getting time for that.
Yeah, could you understand anything in today's class?
No, ma'am.
Not at all.
I
See,
will take that recorded lecture, then I will understand.
because this is related. Now I can't also help you in between. See, Hafsa, what you can do, just understand this much. Uh, See, this at least the linear part, no, because for today's class these things will be used. Look at this second one and the fourth one. You have P is equal to mv. You remember this from your linear part, translational. Linear momentum becomes angular momentum. Mass becomes moment of inertia. Velocity becomes the angular velocity. So when you multiply and combine these, L is equal to I omega becomes the formula. Similarly, kinetic energy is half mv square. That becomes half I omega square. Like this, you have to write the analog of everything. So that, and the way we have conservation of linear momentum, we have conservation of angular momentum. Whatever we have studied, that remains the same. So this is something what we are studying. Try to understand now a bit if you can understand. I know it will be difficult because this is completely different, and it's difficult for me also to relate to you. But you understand today's class. But when you will sit to revise, or after watching the previous videos, you'll be able to understand it better. So don't miss it. Understand it. Still, if you want me to repeat any portion, Hafsa, or you want me to teach any of the previous part that you can link with, so please just let me know in between. Okay?
Okay, ma'am.
Hafsa, when are your exams ending?
Ma'am, now it's end.
What?
Finish. Finish, ma'am, exams.
Exams are finished. How was the physics paper?
Ma'am, actually, I will practice for that questions. I practice all question from all chapter. What are coming exams? Up to work. I practice question answer.
सारे questions कर लिए थे.
Yes, ma'am. From SL Aurora book, I practice. And ma'am,
मतलब
what she gave
exams
only
में जो आ
theory.
रहे थे वही करे होंगे ना
Like
सब.
no, only derivation she gave in paper.
What? Derivations were
All
given.
derivation she gave. All derivation, ma'am.
All of it was derivation based,
Yes, ma'am.
and you didn't see the derivations.
No, ma'am. I knew the formula, so I found it by myself, and it is correct only. I found by derivation I did by myself only.
Okay,
Ma'am, we will get paper tomorrow of physics.
you will get it.
No, yeah, tomorrow I will get that. So, ma'am is said everyone did good. I got out of 70 more than 50. I don't know what.
How much did you get?
Out of 70, more than 50.
More
But
than
she didn't say
50 is it?
exam.
Okay. At least share the question paper. Let me see what kind of paper was it. है ना? भेजना
Okay,
उसे.
ma'am.
WhatsApp पे भेज देना, ठीक है?
Okay, ma'am.
So see, in the second one, L2 is equal to I omega 2. Now see, when we talk about the moment of inertia here, again, moment of inertia, same four things are there. Man is there, platform is there. So their moment of inertia combined is given. I've just written it as IP. IP is not a symbol for anything. And again, this will be M, but new radius, plus MR2, plus this MR2. These are there. And every data is with us. Only what is missing? This omega 2 is missing. Just equate both of them. See, IP plus MR1 square plus that will actually become 2MR square. MR square plus MR square will become 2MR square. Plus 2MR1 square into omega 1 is equal to. This will be IP plus 2MR2 square into omega 2. See, everything is given. You just have to calculate omega 2. Tell me what are your answers you are getting and write this question and try to understand. Nabila, have you understood?
Yes, ma'am.
Write it. Okay, see the next topic is radius of gyration. See, we talked about the center of masses concept, okay? And the mass and the radius we calculated and we used the whole concept I is equal to mr square. Now, radius of gyration is what? See, it can be defined as the distance from the axis of rotation, okay? To which if the whole body means whole mass of the body was supposed to be concentrated. Means if I take, let's say this point can be anywhere. It can coincide, it can be on center of mass also, and it cannot be. So let's say there's a point here, I take a point anywhere, I take a point, okay? Separation is R. So that separation from the axis of rotation is known as the radius of gyration. Okay, so its moment of inertia of the axis of the given axis would be same as with the actual distribution of mass. Means the way you have the concept of center of mass, radius of gyration basically gives you the separation from the center of mass exactly. Before this, when we had the radius for moment of inertia, that radius could be any radius. But this radius of gyration is the one where the center of mass is concentrated. That is your radius of gyration. So in order to differentiate the radius of gyration with the radius of moment of inertia, we take this as K. Here the formula is I is equal to mk square. This becomes the formula where m is the mass, I is the moment of inertia, k is the radius of gyration. So what you do, you have the moment of inertia's formula from the last classes also. You have mk square also. You equate both of them. Whatever will be the value of k, you will get. Like I'll tell you, look at this example. Calculate radius of gyration of a disk of mass m and r. See, by default, when nothing is mentioned, no, we take this as the r-axis. The perpendicular one and through the center one. Perpendicular and through the center. So moment of inertia is mk square and moment of inertia for a disk is mr square by 2. So that's why I said you need to remember these moment of inertia, otherwise you'll face trouble because something you cannot derive every time in the exam, no? Now we equate mr square by 2 is equal to mk square. Mass will be cancelled. K is equal to r by root 2. So K is the radius of gyration, R is the radius. Radius, this one is from your moment of inertia. So like this, mk square, you equate it with mr square by 2 like this. Very easily you will get your answers, okay? Write this first, write the right radius of gyration. We will see some more things and many questions have also come. And I'll also have to check up from your syllabus. I think the moment parallel theorem axis, perpendicular theorem axis, these have been deleted from the syllabus. I'll see that. Please write it. See, the radius of gyration, if we calculate from here, the radius of gyration for sphere of mass m and radius r. So in general, by default, we have to consider a hollow sphere. Solid spheres will be mentioned. So this is a hollow sphere. So moment of inertia of a hollow sphere is, yes, Nabila?
I equal to 2 by 3 mr square.
Correct. 2 by 3 mr square. I is equal to mk square. Equate both of them. 2 by 3 mr square is equal to mk square. Will be cancelled. K is equal to r root 2 by 3. Fine, write this, then we'll discuss rolling motion. See, now we have a rolling motion. Rolling motion basically means you have translational plus rotation motion together. The best example is the example of wheels. In wheels, what happens? The tire moves further also, translates also, as well as it rotates also. So that's why the vehicle moves further. So we won't say the tires are rotating or the tires are translating. Rather, we'll prefer to use the term tires are rolling because they are not just rotating and they are neither just rotating nor translating. They are both rotating and translating at the same time. So that is what we call as the rolling motion. Now we are going to choose 3 points in the two in the peripheral regions and one in the central region. One is this. Let's say this has the center of mass in this direction. This is the center move point, central move point, that is VCM along this direction. And this is the B point with VCM along this direction. Now see, this is in translation, means this is the translational velocity of center of mass. Remember we discussed this in a center of mass, if you remember. In center of mass, first we said position of the center of mass and then I told you velocity of the center of mass. In fact, we discussed acceleration of the center of mass. So this is VCM, this is VCM, VCM. All of these are directed in one side. Now, in rotation, we'll say V is equal to R omega because angular velocity will come. So V is equal to R omega. Both of these are the points. Okay. Now, when you combine, what you get? You have VCM of the mean center of mass's velocity is also there, and R omega is also present. Similarly, for acceleration, okay, one more thing. If I take out, let's say at this point A, if I write down the net velocity, what will it be at the point A? Look, both of these velocities are in the same direction. So it will be velocity of center of mass plus R omega. But if I choose the bottommost point, that is B, they are in the opposite direction. So my net velocity at this point B will be velocity of center of mass minus R omega. That's what we do in the rolling motion. Similarly, we are going to calculate this for acceleration, but first write it, then we'll see for acceleration.
Done.
See the acceleration when we talk about at every point the way we have the velocities present. Here the center of mass will have their accelerations also. Individual accelerations will also have their center of masses. And at every point, as we discussed, the way you have omega r for velocity, the centripetal acceleration, or if you talk about the tangential acceleration, here we have a relationship between tangential acceleration and the angular acceleration. As we discussed earlier, this is alpha r. Now, this is ACM, this is alpha r, this is ACM, and alpha r is situated in the opposite direction. So, at point A, velocity A means here it will be acceleration of the center of mass plus alpha r. Not velocity, acceleration. And at B point, the acceleration will be at B point. This will be acceleration of center of mass minus alpha. So usually you are asked to calculate the net acceleration at these points, A points, B point. This is the B point. So you need to write it similarly. This I'll discuss later. Write it till here acceleration.
Done.
Nabila, just wait for 5 minutes. I'm coming.
Okay, ma'am. Take it.
Yes. See, pure rolling motion, let's discuss. One example is when the car is moving on a concrete road. That's a very great example. Pure rolling means translation and rotational components are the same. Means if I say, let's say there's a tire present, okay? This tire is rotating and it is moving forward also. This tire is moving further also. Let's say this much part that the tire will cover, this much of circumference that this tire will cover, this one, this much, this one, whatever it has to take to move further, whatever it will cover. If I say that 2 pi r or total 2 pi r, whatever it has to cover on rotation, is equal to this length L. Let's say this is some L and this whole circumference with the radius 2 pi r, this is also existing. So what will happen? The rotational component means how much the tire has rotated and how much the tire has moved. These both components are the same. Okay. So this is one thing which you should know. That's known as the classic case of rolling, means pure rolling motion. Here the translational motion is equal to the rotational motion. So distance covered in translation is equal to distance covered in the rotation. Now there can be two cases when rotation is greater than translation or translation can be greater than the rotational motion. See, if tires are stuck in sand, so what happens? If the tires are present and these tires, they are stuck in the sand, so what will happen? The tires will get, the tire will be just rotating. The tire will just be rotating because it won't be able to move further because of the sand. So when the rotational component, this is a very good example when the rotational component is moved. Or you can say when the tires are sliding. If it's a very smooth, shiny road or a surface, tires are present on it. So what happens? Because this car skids off, especially in the skidding of the car, when the car skids off, what happens? Car's tires just move like this without any rotational component. That is when translational is greater than rotation. Okay, then we are just left with kinetic energy. Write about pure rolling. Then let's discuss about kinetic energy.
None more. Done.
Okay, see, kinetic energy in rolling. See, when we talk about the kinetic energy in the rolling motion, we'll have the translational component and rotational as well. So, rotational, we know what's the rotational component. It's half I omega square, while kinetic energy in translation is half mv square. See, if we take half common from both of these, we'll be left with half omega square plus mv square. Now, you know one relationship between velocity and the uh, angular velocity. V is equal to omega r. So here V square will be omega square into r square. Let's put the value. Half I omega square plus m omega square r square. Let's take half, let's take omega square by 2 common. I plus mr square. So like this, these formula you can use for kinetic energy. One last question is left from this chapter. First, you write down this theoretical part. Let's see if time is there, we'll discuss, or in the next class. Have you understood, Nadira?
Yes, ma'am.
Oh, please write it.
Done. Done.
Okay, so yes, one numerical is left. Nabila, I'll discuss this numerical in the next class now because it's a very
Okay.
important question and it will take a lot of time. So we don't have much time. I'll discuss it in the next class because assignments and all are there. And this chapter is done. Okay, I'll start with gravitation. Fine?
Yes, ma'am.
Okay then. Thank you, Nabila.
Thank you, ma'am. Bye. Take care.